course on semiconductor optoelectronics. So, semiconductor optoelectronics. Let us start with the title. Semiconductor optoelectronics. What does the subject matter of this course comprise? So, semiconductor, let's start with the title as such. Semiconductor, we know about what is a semiconductor. What is a semiconductor? And we also see what is optoelectronics. And then we understand the subject matter of this course on semiconductor optoelectronics. What is a semiconductor? We all know what is a semiconductor. Or do we know what is a semiconductor? As the name indicates, is a material which has conductivity between materials which have conductivity between those of bad conductors or insulators, bad conductors and good conductors. In a very elementary fashion that we see, good conductors between bad conductors and good conductors, or metals and insulators. Conductivity between those of bad conductors and good conductors. What kind of numbers that we are talking? Conductivity is 1 over resistivity, inverse of resistivity. What kind of numbers do we talk for bad conductors? Bad conductors or insulators typically have conductivity in the range 10 power minus 12 to 10 power minus 18. Units are Siemens per centimeter. Inverse of resistivity 10 power minus 12 to 10 power minus 18. Resistivity has, as you know, units of ohm centimeter. So this is essentially ohm inverse, Siemens. Siemens per centimeter. And for good conductors, it is typically approximately 10 power 4 to 10 power 7 Siemens per centimeter. Semiconductor materials have conductivity approximately in the range 10 power minus 6 to 10 power 3 Siemens per centimeter. First step, that what is a semiconductor? We are trying to attempt to answer this question. What is a semiconductor? A material which has conductivity between those of good conductors and bad conductors. So the typical numbers for conductivity of semiconductors are this much. But does this qualify a material to be a semiconductor just if it has conductivity between those of good conductors and bad conductors? No. Then it would not have had such important applications as we have today, that the primary applications of semiconductors have come out because of the following, that the conductivity of semiconductors can be varied by orders of magnitude. The conductivity can be varied, conductivity can be changed by orders of magnitude by one, by doping the semiconductor material, by doping, by changing the temperature of the material, as we will see later that the conductivity depends on the doping concentration. Semiconductors are normally doped, p-doped and n-doped semiconductors are used in devices. So doping the semiconductor can change conductivity by orders of magnitude, and temperature, changing the temperature can also change the conductivity, and one can also change the conductivity by illumination. With the light of appropriate wavelength. By illumination with light of appropriate wavelength, we can change conductivity of materials by a very large amount. And this is the primary reason why semiconductors become very important, where the conductivities can be changed by orders of magnitude. So the elementary definition of a semiconductor is materials which have conductivity between those of good conductors and bad conductors, and whose conductivity can be changed by orders of magnitude, by doping or by changing the temperature or by illuminating the material with light of appropriate wavelength. We come to the second part, namely optoelectronics. What is optoelectronics? Optoelectronics basically deals with the science and technology. Of electronic devices, of basically electronic devices, which involve interaction with light. Just to give you an example, for example, an LED, a light emitting diode, is basically a PN diode. A PN diode is an electronic device, but it involves emission. When you pass a current through a forward biased LED, it emits light. And exactly like that, photodetectors, where when light is incident on photodetector, it generates current. It's an electronic device, but involves interaction. Interaction here primarily referred to emission and absorption. Emission and or absorption. So semiconductor optoelectronics therefore deals with devices, phenomena which of electronic devices, basically electronic devices, semiconductor electronic devices, which involve interaction with light or emission or absorption of light. So that is semiconductor optoelectronics. Semiconductor optoelectronics. Let me write again. Semiconductor optoelectronics. I want to spend a few more minutes, semiconductor optoelectronics, on this terminology, because there are similar terms, synonyms or similar looking terms. Optoelectronics, we also have electro-optics, we have optical electronics, terms such as optical electronics. There are books on optical electronics, electro-optics, all books titled Electro-Optics, Optical Electronics, Photonics, Quantum Electronics, Quantum Electronics, and so on. A number of similar looking terms. It is very difficult to give a precise definition of a precise domain. However, as we discussed just now, optoelectronics deals with electronic devices which involve interaction with light. In electro-optics, we basically deal with optical systems or devices where the propagation properties or characteristics of the device can be altered by application of an electric field. Application of electric field. The propagation properties of light through these devices are altered by application of an external electric field. For example, let me give an example of electro-optic modulator, EO modulator. Electro-optic modulator. Usually, these are optical devices, maybe a crystal, through which a beam of light propagates through this light. If you apply an electric field to this crystal, I am showing metallic electrodes here. If you apply an electric field, it is possible to modify the output properties of light. For example, the polarization can be modulated. The application of the electric field here, so this is a E field, leads to variation in the refractive index of the medium, and that can result in variation of the phase of the light. So this is the basic principle of phase modulator. So electro-optic modulator is a device which is an electro-optic device. So electro-optics primarily deals with optical devices and optical systems where the application of an external electric field modifies its properties. Similar definition holds good. There are similar terms as acousto-optics, and magneto-optics. All effects are discovered in the 19th century. Magneto-optics. Acousto-optics refers to optical systems where the characteristics are altered, where the propagation properties are altered by application of an acoustic field. If you replace electric field here by an acoustic field, we deal with acousto-optics. What is this acoustic field? For example, if you apply an RF, to a crystal, for example, so you have a crystal here, and there is a transducer, absorber here, there is a transducer, to which you apply an RF, which forms standing waves in the medium. There are mechanical waves which propagate through this medium, which form a standing wave, and due to this there are compressions and rarefactions frozen into the medium, act like a phase gradient, and then an incident optical beam here can get diffracted into particular direction, satisfying certain phase matching conditions, and this was the original arc, and diffracted to an angle. This is called Bragg diffraction. There are two important effects which are Bragg effect, Bragg diffraction, and Raman-Nath diffraction. Raman-Nath diffraction. In Raman-Nath diffraction, we get multiple diffraction orders, whereas in Bragg diffraction, if the phase matching condition is satisfied, then we have the entire energy can get transferred to a particular diffraction order. So these are properties, these are effects which are discussed in detail in acousto-optics. Similarly, magneto-optics, if you alter this definition and replace the electric field by magnetic field, what you have is magneto-optics. So magneto-optics deals with optical systems where the propagation properties are modified by an applied magnetic field. A very important effect which we are aware is the Faraday effect. Faraday effect. Faraday effect, where you have a linearly polarized beam, let's say a linearly polarized beam, traveling through this optical medium. If you apply a magnetic field H, then the polarization state gets rotated to an angle theta, and this angle is proportional to the strength of the magnet. We are aware of this, the Faraday effect, where the state of polarization is rotated due to an applied magnetic field. There are several applications of both Faraday effect and Bragg diffraction. So acousto-optics and magneto-optics and electro-optics, all these three are known well in the 19th century. We come to some of the other terms. What is this optical electronics? Before that, let me see what is quantum electronics. Quantum electronics is a branch of science where we study the interaction. It is a branch wherein we study the science and phenomena which involve interaction of radiation with matter. Interaction of radiation with matter. Quantum electronics primarily deals with the study of devices and phenomena which involve interaction of radiation with matter. The most important device, a quantum electronic device, is a laser. Laser is a quantum electronic device. Nonlinear optics, which have several effects. Nonlinear optics is also part of quantum electronics, so which involve interaction of radiation with matter. What is optical electronics? In the 19th century and in the early 20th century, we had electro-optics, acousto-optics, magneto-optics, optics itself, polarization, quantum electronics, which included lasers and nonlinear optics, quantum electronics. Including nonlinear optics, all the study of all these together, the subject matter which comprised study of all these are called together as optical electronics. Optical in the 1970s. The famous book of Yarin, Optical Electronics by Yarin. The first edition came in 1970. It's widely used textbook on optical electronics, which described all these effects and other propagation properties of light through medium. In the 1980s, the light wave technology, developments in light wave technology rapidly progressed due to the advent of semiconductor lasers and optical fiber communication. So, in the 1970s, developments in semiconductor lasers, photodetectors, optical communication. So both 70s to 80s, optical communication, optical fiber communication, fiber optics, optical signal processing, rapid developments in these areas led to light wave technology becoming an almost independent branch, light wave technology becoming an important branch technology, light wave technology. Rapid developments in the light wave technology led to an entire branch analogous to electronics, which is called photonics. In 19 photonics. So photonics encompasses optical electronics plus the earlier optical electronics and all the modern communication technologies which are included in light wave technology here. So this plus this together was the term was coined as photonics, which is analogous to a branch, analogous to electronics, photonics in the 1990s. One of the first books was Fundamentals of Photonics by Saleh and Tish, widely used as a textbook. So this much about the terminologies, various terminologies that are prevalent, and today the branch is very widely known as photonics, complete science which involves interaction of photons and electrons or interactions of photons and atoms. Let me go a little bit further. I am trying to present the context. In this lecture, I am presenting the context, scope, and contents of this course. So, why study semiconductor optics? Why study semiconductor optics? Try to address this question, why study semiconductor optoelectronics. This course here This course is a core course of the program on optical communication, optoelectronics and optical communication. It's a core course. Therefore, let me take an example in the context of optical communication. If you take a simple optical communication link, then you have a transmitter and link here, link and transmitter, receiver and the communication link. If it is optical fiber communication, then this link is an optical fiber. It could be a two-way link or optical fiber. So then it becomes optical fiber communication. Transmitter, receiver and optical fiber. Now the transmitter here, if we use this optical communication is used, optical fiber communication is used for data as well as voice, data and voice, including all video data, digital data as well as voice. Voice, if we look at voice, that is the normal voice communication, telephonic conversation, then voice is first digitized, because all communications today are digital communication. So digital signal, voice is digitized. For example, you have a NRZ pattern. So this is digital 1, here is a digital 0, this is 1, 1 and 2, 1, 1. A digital sequence, a signal which is, so the voice is first digitized and here is the digital signal. So the digital signal, so in this transmitter, this comprises of all the electronic processing part which converts the voice signal into a digital signal, and the last component here is a light emitting diode or a laser diode, where the bias current I is modulated by the same digital stream. So 1, 1, 0, 1, 1. So the bias current through this laser diode, LD is a semiconductor laser diode, modulated, and therefore the laser diode output gives pulses corresponding to digital ones and no pulse corresponding to. This is light pulses now. This gives out light pulses in accordance with the current signal, varying current signal. So this is a digital 1, digital 0, 1, 1 and 0. So the last component here, which the light output is then coupled to the optical fiber. Light output is coupled to the optical fiber here and transmitted towards the receiver. So the last component here is a semiconductor laser diode or a light emitting diode. Similarly, at the receiver, the received optical signal, the incident optical signal, is incident on a photodetector, on which the incident signal is incident, the optical signal is incident. There is a photodiode which generates a reverse current IP here, which again corresponds to the digital signal that we have transmitted. The photocurrents generated due to the incident optical pulses are of the same pattern as that of the original. Of course, pulse shaping and other things have to be processed, which will be processed in this receiver here. The receiver contains all the electronic devices and signal processing devices, but the first component here is the laser diode, the photodetector, and the last component here, the first component is the photodetector and the last component here is the laser. So, in the context of a simple optical communication system, we need a transmitter, a laser diode is a transmitter and a photodetector is a receiver. So, which are semiconductor optoelectronic devices. So, in the context of optical communication, this is a simple example. Actually, on the link there are other amplifiers, optical amplifiers, which will also involve photodetectors and laser diodes there. But this is from a communication perspective. But optical communication is not the only application, because we know that semiconductor lasers, laser diodes, photodetectors, LEDs are widely used in consumer electronic and consumer optoelectronic products, such as, for example, in information technology, we have laser printers, CD drives, laser printers, barcode scanners, and number of applications. The laser pointers, the CD players, DVDs, everywhere you need optoelectronic components. A large consumer electronic market exists where optoelectronic components are widely used. Optical communication being just one. Historically, one of the earliest optoelectronic component is the optocoupler. Let me discuss this, the optocoupler. This was in the early 1970s. Optocoupler is basically comprised of component like this, and a photodetector. It's a coupler. As for historical, when people had electronic circuit boards, these are circuit boards, which had to be connected but had to be electrically isolated. So there are two circuit boards, which had to be electrically isolated. When you want complete electrical isolation. This is an electronic circuit board. It's a PCB, let's say, printed circuit board, and there is an electronic circuit board here, which requires complete electrical isolation. There are certain processing circuits which have ground as the common terminal, whereas some of the other circuits which have positive or negative, the main line, the main supply as the common terminal. Then in such cases you need complete electrical isolation. And one of the components which is used was optocoupler. It was very easy because the LED here, it was based on LED and photodetector. So this was an LED, light emitting diode, and this was a photodiode. So the LED would give, depending on the current I through the LED, it would give out light, yeah, and the photodetector will generate the same current I, or current proportional to the I here. It will generate the photocurrent P, which will then go to the next circuit board. So the photocurrent generated here is proportional to the current through the this was one of the earliest optoelectronic component optocouplers, widely used in electronic circuits. But today, a similar thing, which is on a much more different scale, is used for high speed, high density optical interconnects. High density optical interconnects. Optical interconnects. For this reason, I thought of mentioning this earliest simple device optocoupler, that a renewed interest in this kind of coupling between two circuit boards which handle very large high speed optical interconnects. That is, you have a MOS device here and you have a CMOS device here. There is a CMOS electronics, CMOS circuit board. There is another CMOS circuit board. Very high speed electronics, gigabit data speed electronics. You need communication between them. One of the ways, of course, you could have electrical wires, large number of electrical wires, but the electrical wires will have their own losses and inductance. At very high speeds, very high data rates, it becomes prohibitive. And one of the ways which is used now, which is being developed, is optical high speed, high density optical interconnects, where you have an optoelectronic chip. The electronic circuit board is connected to an optoelectronic, so OE chip here, and there is an OE chip here, optoelectronic chip. OE chip, what is this OE chip? OE chip is a chip which contains optoelectronic components such as laser diodes and photodetectors, and you can have communication between these two OE chips, high speed communication in the optical domain. So this is optical communication. Optical communication. It could be free space optical communication, or it could be this OE chip is connected to this OE chip through optical fibers. Such chips are being, such high density optical interconnects are being developed. So the advantage being, at very high speeds, there is no deterioration of the data. There is no deterioration of the data if you handle it in the optical way. A higher version of this includes chip to chip. So chip to chip communication, direct chip to, this is OE chip, this is OE chip and OE chip, which talk to each other directly. The sources here are monolithic pixels, and the detectors are photodetectors. So pixel is short form for vertical cavity, surface emitting, you can draw an array of pixels on the chip which emit vertically upwards or which emit vertically, and you can have an array of photodetectors here. In both array of pixels and photodetectors, array of pixels and photodetectors can have free space chip to chip communication at very high data rates. That's tens of gigabits, and several of them, many of them, is what is being developed now, and therefore this is original. It's a highly improved version of the original optocoupler. Okay, so let me come to the context. This is the context of the course, and let me come to the scope of this course. It is first. It's a first. By first course, I mean most of the times we start with fundamentals. Start with fundamentals. Elementary concepts. So elementary concepts. We start with fundamentals and elementary concepts and build on it. So it's a first course which would require background of optics, some background of optics, EM theory, electronics or semiconductors, little bit of quantum mechanics, or simply a first course for undergraduates who have done a course on applied physics, an undergraduate program on applied physics, or first year undergraduate level, a first year undergraduate level of background of optics, EM theory, semiconductors and quantum mechanics. This is what would be required. It's a first course which could be for senior undergrads, it could be for senior undergrads or for first semester masters. So that is the level of course, and as we have here, the students who take this are from various backgrounds. They are from electrical engineering background, optics, physics background, applied physics background, and also some people from mechanical engineering background. So we really do not require any specific prerequisite other than some basic concepts in the area of optics, electromagnetic theory and quantum mechanics at the first year level. So let me give you the contents of this course. The course will have 4 parts. The first part, we review semiconductor physics for optoelectronics, that is essential semiconductor physics for optoelectronics. So we start with energy bands in solids, the EK diagram, the band structure, the density of states in quantum well structures. A little bit of quantum mechanics would be required here, but we will discuss from the basics. Then we will go over to occupation probability of carriers and carrier concentration in semiconductors, the carrier concentration and its dependence on the Fermi level, the quasi-Fermi levels, which are very important in optoelectronic devices, semiconductor materials. We briefly discuss essential semiconductor materials for optoelectronics. Semiconductor materials will not be able to go into details of all semiconductors, but those which are widely used in optoelectronics. Just to name a few, silicon, germanium, gallium arsenide, indium phosphide and so on. We then discuss semiconductor heterostructures, lattice matched layers, the need for lattice matching, strained layer epitaxy, which usually have certain advantages and which also deal with quantum well structures, or the layer thicknesses are small enough so that we discuss quantum well structures. We also discuss band gap engineering, that is tailoring of band gap, various techniques for tailoring of band gap, and then finally in a device we have PN junctions, Schottky junctions, that is junction between metal and semiconductors, and ohmic contacts. So we will discuss the last part here, namely PN junctions, Schottky junctions on ohmic contacts. from a point of view of the final device and briefly overview fabrication of heterostructure devices. There are several techniques which are used. We will briefly overview fabrication of heterostructure devices. We will not again go into the details because there are full courses on the fabrication technology of semiconductor devices. This is part 1 of the course. So, approximately the first 15 lectures will cover most of the essential semiconductor physics or device physics. In part 2 of the course, we will discuss light emission, absorption, amplification and modulation, approximately 10 lectures. We start with the interaction of photons with electrons and holes in a semiconductor. We will discuss optical joint density of states, probabilities of emission and absorption, rates of emission and absorption, amplification by stimulated emission, which is the basic principle for laser action, and we discuss the laser amplifier, absorption spectrum of semiconductors, gain and absorption in quantum well structures. One of the important devices based on the absorption spectrum of quantum well structures immediately follows, namely the electro-absorption modulator. We will also discuss the principle of operation and device configuration here, and in this part finally we conclude with semiconductor laser amplifiers or SOAs. In part 3 of the course, it is part 3 or different modules, these can be treated as different modules. Semiconductor light sources. We start with injection electroluminescence, light emitting diodes, device structure and output characteristics, modulation bandwidth and materials for light emitting diodes and their applications. Then we come to laser basics, in particular semiconductor lasers, the device structure and output characteristics. We discuss single frequency lasers, the distributed feedback and distributed Bragg reflector lasers we will discuss here. Also the vertical cavity surface emitting laser, about which I mentioned just now, and we will also discuss quantum well lasers and practical laser diodes, laser packages and handling of these devices. In the last part of the course, we will discuss about semiconductor photodetectors. This is a small part because most of the characteristics and device structures have already been discussed in the earlier parts. So, directly we go over to general characteristics of photodetectors, the impulse response of photodetectors, and one of the simplest photodetector being photoconductor with the specific applications. We go to semiconductor photodiodes, two important configurations being pin diodes and avalanche photodiodes or APDs, their structure, materials, characteristics and device performance. We briefly discuss other photodetectors such as phototransistors, solar cells and CCDs. As an epilogue to these 4 parts, finally I would like to summarize and give a talk on photonic integrated circuits or PICs. The reference books, here are some of the references which are listed. There are large number of books in the area of optoelectronics. So, I have listed some of the important textbooks, namely Fundamentals of Photonics by Saleh and Tisch, chapters 16 and 18. This covers most of the photonic sciences and technologies, but chapters 16 and 18 is primarily deals with the semiconductor optoelectronics. Yariv and A, Photonics, Optical Electronics in Modern Communication, the 6th edition of the original book Optical Electronics of the 1970, the first book. Here again chapter 15 to 17 would be useful. More recent book by Gion, Semiconductor Devices for High Speed Optoelectronics, and two classic books on semiconductor optoelectronics. The first books exclusively on semiconductor optoelectronics by Pallab Bhattacharya and Jaspreet Singh. Here I have listed them, although they are dated, but they are still very useful in terms of fundamentals and the early developments in optoelectronics. So I would also strongly recommend you to go through these two books, the basics in semiconductor optoelectronics. So these are the course contents, and as I said, the course will have 4 modules, which I have written as part 1, part 2, part 3 and part 4. The first part being a review of essential semiconductor physics for optoelectronics. Those of you who have had a first course already in semiconductor physics can even go over directly to part 2 of the course. I think with this I will stop this first lecture, and we start with the part 2. Almost all lectures will follow as per the course contents listed here. So we will start with the part 1 of the course, that is review of semiconductor physics. In the next lecture, we start with energy bands in solids, the EK diagram. Thank you.